Okay, hello everyone, and welcome to the last holotube of the year. We're very happy to have Michael Landry from MIT, who will tell us about non-equilibrium coset construction. Please go ahead, Michael.
All right, well, thank you for having me. Very happy to be here. So today I'm going to talk about non-equilibrium effective field theories and a method for constructing them known as the Coset construction. So essentially, this is the outline of what I'll be talking about, but let's just dive into it directly. So why bother with this non-equilibrium Coset construction? So non-equilibrium effective field theory is a way to describe dissipative, typically condensed matter systems with a Lagrangian formalism. So usually Lagrangian formalisms only allow for conservative systems, but if you define it on the Schwinger-Keldysh contour, I'll get to that in a little bit, then you can systematically take into account dissipation in a controlled derivative expansion. You can do Feynman diagrams, so it's a rather useful technique. However, historically, until fairly recently, there have been a fairly limited number of condensed matter systems that one can describe. Typically, they're in fluid phase. Maybe magnetohydrodynamics, maybe a diffusion system, but it's more or less just fluids of some variety, with a couple of exceptions here and there. But there's a way to classify condensed matter systems based on spontaneous symmetry breaking. And from high energy physics, we know that the Coset construction, well, it has been applied to zero temperature condensed matter systems when Poincare symmetry is spontaneously broken. But now I want to basically upgrade this Coset construction to account for non-equilibrium effective field theories, and in doing so, greatly expand the number of condensed matter systems that can be described. So the main thing that I'm going to focus on in this talk is solids, just as an example to show you what can be done, but various other things can be done, such as superfluids, magnetohydrodynamics. This requires higher form symmetries, which I don't really touch on, pneumatic liquid crystals, smectic liquid crystals in various phases. So it has a wide range of applications. So the Coset construction essentially just takes spontaneous symmetry breaking as your input and spits out an effective field theory of Goldstone bosons. So when you can read in Weinberg how this is done when only internal symmetries are broken, but when space-time symmetries are broken, you need to take into account some extra features. So you basically just parameterize the most general Coset element of nonlinearly realized symmetries. This is tau denoting all of the broken generators and p bar denoting unbroken space-time translation symmetries. The reason we call these nonlinearly realized is because translations are nonlinearly realized on coordinates, while they are on fields. This is sort of just a hand wavy reason. The real reason is just because it works. So this is the way that you parameterize your Coset. You then go and calculate the Morar-Cartan one form, which transforms covariantly under all of these symmetries. And you can basically parameterize each of the terms. You can expand it in terms of each term is proportional to some generator. So this is an element of the Lie algebra based on various math theorems. We call this first term the Vielbein. It basically serves as a Vielbein. You can construct an effective metric out of it. In particular, you can construct the invariant integration measure. Typically, it just turns out to be 1. Then you have covariant derivatives, which transform covariantly. And then terms that are related to these unbroken non-translation, non-space-time translation generators essentially transform as connections. And so you can take higher order covariant derivatives using these connections in this sort of a form. And finally, when space-time translations are spontaneously broken, there are sometimes extra Goldstone bosons that can be removed. For example, if you have a superfluid that spontaneously breaks boosts, it also spontaneously breaks time translations, but there are no obvious boost Goldstones. The boost Goldstones theorem is still satisfied. You can remove these Goldstones in favor of other things. So the Goldstone theorem of this one-to-one correspondence of broken symmetries and Goldstone bosons is now thrown out the window when you have broken spacetime. So the Schwinger-Keldysh effective field theory to describe non-equilibrium systems. On the Schwinger-Keldysh contour, you have to, I won't go into any great detail, but essentially if you have your equilibrium state as a thermal density matrix, then just as an ordinary state evolves with one copy of the time evolution operator, a density matrix will evolve in time with respect to two copies of the time translation operator. And so you can introduce double sources, and you essentially have to introduce doubled fields when you construct these effective actions. And then you usually call these fields 1 and 2 for the one contour and the two contour, or 1 flows forward in time and 2 flows backward in time. And you take these symmetric and anti-symmetric combinations. Symmetric here essentially can be treated as a classical field, roughly speaking. This anti-symmetric combination encodes information about noise and statistical fluctuations, quantum fluctuations, that sort of thing. But they all vanish on the equations of motion. So it's only in correlators that these appear. So in order to have conserved energy momentum, it has been discovered, proposed by various groups that including my current advisor at MIT, Hong Liu, that you need to, oh, say again? I
don't think there was any question, sorry.
Got it, no problem. So you have to define it on these world volume coordinates. These are just an auxiliary space-time, and then you embed these into the physical space-time with x mu, where s is 1 or 2, depending on which contour of the Schwinger-Keldysh you're on. Then finally, to account for the fact that your equilibrium state is a thermal density matrix, which it typically will be, I'll just assume that as a blanket statement for everything I say, you need to impose the so-called dynamical KMS symmetries. So the KMS relations exist for generating functionals, and they can sort of be understood to be symmetries of ineffective action. And this will, it's a certain kind of symmetry, so it's something that you can implement at the level of an EFT, and it basically ensures that your equilibrium state is thermal. Oh, yeah, okay, I'll move on. So here, it has been postulated that for fluids, you have these essentially gauge symmetry in the sense of redundancy of description, diffeomorphisms that are spatially dependent and temporally independent. So there's no, M here runs from 0, 1, 2, 3, I runs from 1, 2, 3. So there's no phi 0 dependence in these. So I'm going to postulate that Goldstone bosons, they're not technically goldstones, but I'm going to call them goldstones because they look like goldstones. Essentially, Goldstone bosons exist for unbroken generators in this effective field theory. The sort of hand-wavy explanation for this is that any sort of microstate of a thermal bath will spontaneously break all symmetries. So you might sort of expect that goldstones will exist for all symmetry generators. But the way that they're differentiated from genuine goldstones is that they have this extra shift symmetry. So if epsilon here, where S indicates which leg of the Schwinger-Keldysh contour exists, then these, I'm going to call them unbroken goldstones. These unbroken goldstones have this gauge shift symmetry where they get multiplied by some arbitrary time independent function. So this will reduce their, this will fundamentally change how they interact. It will make them not satisfy a Goldstone theorem. And so that's basically just a postulate that I will assume. There's no proof of this, but it works for a large range of cases. So we're just going to proceed and assume that this is the case. So these are the symmetries, emergent symmetries that we're going to assume. So now let's take a look at the non-equilibrium coset construction. Here we're going to let P bar mu once again represent unbroken space-time translations. TA are other unbroken generators, and tau alpha are the broken generators. So all symmetries can be parameterized in terms of goldstones or these fake goldstones that have these shift symmetries in the following way. So notice that this is a bit different from here, this example where we had only the broken goldstones and then we had just coordinates here. Now what we have is coordinate embedding fields, and we have the broken goldstones, the proper goldstones, and then these unbroken goldstones, the fake goldstones that have shift symmetries. But we can proceed in a similar kind of manner. We compute this Maurer-Cartan 1 form, and once again, it will be expressible as an element of the Lie algebra. And we're going to parameterize these in the same way. So this E is once again the Vierbein or Vielbein in general dimension. Covariant derivatives are here, and then we also have these connections. So there are various covariant building blocks because we have these time-independent shift symmetries. Anything where M is set equal to 0 will behave in a covariant or invariant way. Also, because these shift symmetries are the same for the 1 and 2 contours, right? So for S equals 1 or 2, these transform the same way. If you take differences of gauge connections, then those also transform covariantly. And then you can take covariant derivatives in these sorts of forms. And finally, if you impose the dynamical KMS symmetries to ensure that your action exists at finite temperature when in equilibrium, then you find that your action factorizes into 2 ordinary actions at leading order, typically. Not always, but typically. So essentially, if you want to deal with 0th order hydrodynamics and you have this non-equilibrium effective field theory for fluids, then you can essentially just represent it as this factorization, and then you can go slightly higher order in the derivative expansion, this phi a to the 3rd. A fields here just based on derivative counting count at higher order in derivatives, and so can be neglected. Okay, so now the range of inverse Higgs constraints, which remove extraneous goldstones, can be vastly expanded. So before, inverse Higgs constraints would remove a proper unbroken goldstone in favor of an unbroken goldstone, because that's all there were. And it's related to this algebraic condition. So if you have an unbroken translation and some sort of broken generator, and the commutator of these gives rise to some sort of terms over here that involve some other unbroken generator, then you can impose an inverse Higgs constraint and remove an extraneous goldstone. There are other examples of how this can work, though. I gave them the terms thermal inverse Higgs and unbroken inverse Higgs. So the thermal inverse Higgs is when you have remove a broken goldstone in favor of an unbroken goldstone. And this happens when you have a commutator that gives rise to an unbroken translation generator. Unbroken removes an unbroken goldstone in favor of another unbroken goldstone, where you have this commutator of P with some unbroken generator gives another unbroken translation generator. And then it appears that we can't ever remove a broken goldstone in favor of an unbroken goldstone. Sorry, I miswrote this here. So there are 3 possibilities. This is the, we can never remove an unbroken goldstone in favor of a broken goldstone, because there's this commutation relation is impossible. Basically, these 2 generators are unbroken. And so it's impossible to have the commutator of 2 unbroken generators which form a group to create something outside of the group. However, we will see that there's a non-algebraic inverse Higgs kind of constraint that can be imposed in some specific circumstances that will be relevant for solids. So now let's get into the construction of a solid. And let me pause at this stage just to see if there are any questions, because I just threw a lot of stuff at at you. So if there are any questions, I'd be happy to answer those now.
As I said before, don't be shy and just ask questions. Just unmuting yourself.
Okay. Well, if you have
yes.
Oh, yes.
Yeah, I have a short question, which I guess this is a point that I could never. You insist on this KMS condition.
Sure.
But if you have a viscosity or the whole system is not fully in equilibrium.
Right.
So the whole effective theory cannot be entirely invariant under the KMS condition, right?
So the generating functional the generating functional has the exact KMS condition, because even with real time or like time dependent correlation functions, your equilibrium state is still thermal. So the KMS condition doesn't mean that your system is in thermal equilibrium or approximate thermal equilibrium. All it means is that the density matrix that you have as an input when you compute your effective field theory is a thermal state. So it does not ever assume any sort of approximation. This is a truly exact symmetry, emergent symmetry of your effective field theory. And so it doesn't matter that including sources takes you out of equilibrium, as long as your initial state is equilibrium, it holds.
Thanks. Okay.
Okay, so let's now look at solids. So the solids spontaneously break boosts, they spontaneously break translations, and they spontaneously break spatial rotations. They do not break time translation. I'm going to assume solids without a conserved U1 charge. This is a little bit unphysical, but it's useful just for pedagogical reasons. That'll just complicate matters. So even though solids, let's say specifically crystals, spontaneously break spatial translations, there's still on a large scale, if you only have access to infrared observables, you can't really see that there are these individual atoms. So there appears to be this large scale homogeneity. Now, the way that we account for this in effective field theories for zero temperature solids is to introduce these additional QI variables, which are internal U1 symmetries that are spontaneously broken, but whose diagonal subgroup with the ordinary spatial translations is unbroken. So spatial translations are broken, QI are broken, but their diagonal subgroup is unbroken. But these QIs are not really like proper UV observables, so they're going to behave a bit differently. For the moment, I'm just going to treat them exactly the same as the Poincaré generators, but I'll explain in a bit how they can be actually a bit different. So, right, I'm going to use K for boosts, J for rotations, and then these P's here for translations. So we parameterize the coset in the usual way. And if you compute the Morar-Cartan 1 form, you can find that it has this form where here lambdas are just the compact way of writing this boost term here, and R is a compact way of writing this rotation term here. Now, the exact form of these things you don't need to take notes on. It's just putting there for future reference. But the point is that we can now use these building blocks to construct an effective action. So it turns out that we have the possibility of imposing inverse Higgs constraints. And the inverse Higgs constraints that we get just by looking at the algebra of the Poincaré group is these things. And they can be used to remove the boost goldstones and the rotation goldstones. And this aligns with more or less what you would think of when you think of a solid, because all you have is these sort of translation deformation. So you only have these translation goldstones, even though it spontaneously breaks boosts and rotations. And you can solve the first inverse Higgs constraint through a bit of tedious algebra to find an expression that solves eta in terms of derivatives of the of this Goldstone for translations. And so that means that anytime you have eta showing up in your action, you can replace it with a higher order in the derivative expansion Goldstone. So that means at leading order, when you can impose an inverse Higgs constraint, you can just kill all terms that have eta, because those would get pushed to higher order. Once you go to higher order, then you, of course, need to take them into account. Then the second constraint, the fact that this pi here is supposed to have a subscript of k on it. Essentially, it just tells you that the symmetric part of this derivative can be expressed in, is the only non-zero part and can be expressed in this following way. Here, this yij is sort of, it tells you the deformations of the solid in terms of all of the various deformations that you can make of the lattice. And here G is the, essentially, well, is the inverse of the pullback metric GMN, which is represented like this. So GMN is the metric on the phi spacetime, and eta is the, of course, the metric of Minkowski. All right, so now we can have our covariant building blocks. We can now construct our invariant building blocks. So at leading order, I mentioned earlier that anytime you have one of these m's turns to a 0, because we have these time-independent shifts, that becomes an invariant or covariant building block. So we have G00 as an invariant building block. We have Yij as another invariant building block, and then we can contract E0 mu. Oh, this here is supposed to have it's supposed to be nabla mu pi I is equal to this object here. So we already have this y object, but the new object that we get here is this d naught psi j. So we have this new object zi. So the solid effective action at leading order is now just the most general thing that we can write down in terms of these three building blocks. So we have this invariant measure, which comes from, it is furnished by the Coset construction. And then we also have just a generic function P, which ultimately can be interpreted as the hydrodynamic pressure, but I won't get into why that is. That depends on Yij, Zi, and G00. Now, it turns out that if you're careful about what you're doing and you look at the thermodynamics, you can find out that the local temperature is given by 1 over square root minus G00. So we have a local temperature dependence. We have this solid matrix that tells you various deformations. It tells you about the shear and pressure waves if you expand to quadratic order. Then we also have this Zi thing, which is a little bit unusual. Essentially, what this does is physically, the thing that we've constructed is actually a fluid plus lattice. So we have this fluid that can flow independent of a lattice. This is recognizable from those of you familiar with second sound as the sort of substructure of how second sound is built in solids. So you have, if you can have basically a thermal bath of solid phonons, then you can excite waves in that bath that behave as a fluid. And you can also have lattice waves. This is a small minority of solids. So we want to, in some cases, have second sound. That's very nice. But not in all cases do we want to have second sound. So here, the propagation of the second sound mode is closely related to the conservation of Qi. So it's a little weird that we would insist upon this conservation law, given that Qi are these fictitious symmetries that only exist in the deep IR. Now, you would say that Goldstone's theorem, if we have these symmetries, then Goldstone's theorem is going to tell us that we have this conserved quantity, and maybe they're approximate symmetries, so they're approximately conserved, but as far as we can tell, they'd be conserved. This is true at 0 temperature. At finite temperature, it actually no longer becomes true. And in order to ensure conservation of charges, you need to make your these Goldstone type modes Stuckelberg fields. which is automatically imposed at the level of the Coset construction. But in order to have, so the pi i's that are the goldstones of these here, you have pi 1i and pi 2i for the two contours. So each of those, there's only one copy of the U1 symmetry. So both of these will shift by the same amount. So if you take the anti-symmetric combination of these two things, then you can get an effective action that has extra terms that don't involve derivatives. So let me be more concrete with this. Let's now, we have this action here. This is just an ordinary
Michael?
action. Yes.
Can we just go back for a sec? Can you explain
Absolutely.
the QIs?
The QS, right. So if you spontaneously break spatial translations, then the action that you get out of this, there's no reason to expect large scale homogeneity. Like if I look at this part of the solid or this part of the solid, I'd expect them to look vastly different if spatial translations are broken. So the purpose of introducing these QIs is that they basically tell you that on large scales, your system looks in some approximate infrared sense homogeneous. So you can think of this as if you put lattices, this doesn't work for an amorphous solid, but it works for a lattice structure. If you think of lattices put in place, you're breaking translations down to a discrete subgroup. But if you zoom out, then that discrete subgroup starts to look continuous again. And so that approximately continuous translation that is now unbroken becomes this unbroken linear combination of P and QI. So you can, I don't have this published anywhere, but if you do this for a 0 temperature perfect crystalline solid, you'll find that in the IR, these QIs emerge as exact symmetries of your action, which is surprising. Does that?
And there's no, I guess there's no, do you know what is the realization of the UV translations into these QIs? Is this something that can be written down?
Oh, sorry, could you say that again?
Is it possible to write down how the UV translations, the lattice discrete translations, are realized into the QIs, or is this?
Yeah, I mean, it's basically that you just do discrete space-time translation so that you just jump from one lattice site to the next, and these are preserved. And so to write down the actual charge generator, I don't quite know how to do. I only know how to do it at the level of writing down an effective action. But there may be.
But it's not going to be something as simple as like acting with a UV lattice translation generator is equivalent to acting with one of these emergent IR. Or is it?
It may be. I don't know. It might be. In fact, it probably is. I don't want to say definitively yes, because it's been like a year or so since I've actually looked at this carefully. It's something along those lines. Basically, so they were initially just postulated as pragmatic symmetries, but we've done some work to make that less pragmatic, but still unpublished. Essentially, they just sort of magically emerge because you have this this unbroken subgroup that's discrete, but then when in the deep IR looks continuous.
Let me maybe ask another question.
Mm-hmm.
The reason I was asking this is I've been reading these papers by Sentel and Dominic Els, on the relation between UV and IR symmetries, and also talk about how UV symmetries in thermal liquids are realized in the IR.
Mm-hmm.
And yeah.
Yes, I regrettably don't know a great deal about these things.
Okay.
Yeah.
All right. Thanks.
Okay. Okay, well, thank you for the question. So let's look at the action. We've constructed just an action for simplicity, ignoring the fact that there are these 1 and 2 fields. We've just constructed one ordinary action, which I will justify with this claim that you can write it as this factorization. But if we want to write it in terms of advanced and retarded fields, these double copy on the Schwinger-Keldysh contour, then we basically, at leading order, can define this action I, which is defined on the Schwinger-Keldysh contour, as this difference between S1 and S2, where S1 depends on fields on the 1 contour, S2 depends on fields on the 2 contour. Then expanding in terms of advanced fields to linear order, we find that it takes the form of this stress energy tensor times this object involving a derivative of an XA field, and this these 3 conserved U1 currents multiplying this derivative of psi A. But under these QI transformations, psi A is actually invariant. And since it's not a real symmetry of the UV, it's actually legitimate to include psi A as a building block in our effective action, which would kill the conservation of these J objects while preserving the symmetry. So essentially what we do is we write down the most generic action at leading order compatible with these, with the dynamical KMS symmetry. That's why we have this particular structure here. So you still have the T mu nu conservation. And now when you compute the equations of motion for psi AI, you find that J I mu is no longer conserved, but it has a lack of conservation, which is related to this M object. So at this point, if we're in the really deep IR, then at the level of the derivative expansion, this is actually the leading order term. So we can integrate out these psi's, and we can ignore these terms when we do so, because again, this is the leading order term. And so what we find is that the time derivative, this is the phi I derivative, or sorry, phi 0 derivative of psi I, is equal to 0, as is the psi A term, psi AI, it should be. At this stage, we've now successfully entirely eliminated these psi A's, and we've eliminated these psi I's enough that we can now gauge fix phi I is equal to psi I. And with this gauge fixing procedure, we can, in effect, remove these psi I's. So now we've entirely removed the goldstones associated with these Q's. And so this is the kind of non-algebraic inverse Higgs constraint that I was talking about before. Right, so there's no algebraic reason why this can happen. However, it just happens that the symmetries conspire in such a way that with gauge fixing, you can, in fact, entirely remove these things on the equations of motion. So now the only fields that are left are these X mu fields. And we have these, the remaining diffeomorphism symmetries are just these time-independent shifts of the time coordinate and the rigid spatial translations that are inherited from the translations that act on psi I, which are these. So what we get now is, well, now that we remove these psi I's, we can once again work with just a single copy of the action. And when we impose these non-algebraic inverse Higgs constraints, this G00 component remains exactly the same. Yij gets converted into the spatial components of the inverse metric, pullback metric. And Zi is just sent to 0. In fact, this condition, partial knot of psi I equals 0, is just exactly Zi equals 0. So I began by saying that Zi was responsible for this second sound process. Now it has been successfully removed by killing the conservation of these quasi-physical charges Qi. And we arrive at an action that now is drastically simplified and has no second sound. It's drastically simplified in the sense that we've killed 3 of the fields through this inverse Higgs type constraint. Now notice that this inverse Higgs constraint that we imposed here is only legitimate if these Qi terms are not conserved. If these were somehow UV symmetries, then this would no longer be allowed because this term here wouldn't be allowed, and these would just be, there would be no way to derive this kind of equation in a way that would be solvable and gauge fixable in a way that would remove these psi i's.
Can I ask another question?
Yes.
So let's try to think, I want to think about a slightly simpler case, which is just internal U1 and superfluid.
Okay.
So there's also an emergent symmetry, which is the conservation of the winding number, which combines with the usual U1 and gives you second sound. Now that symmetry, it's anomalous. So in a sense, it's not exact.
Yes, I agree. However, in order for it to be, for this non-conservation to matter, it's basically the U1 charge here describes the conservation of, say, helium atoms. So in order for this U1 symmetry, if we could include terms like this that would take into account the fact that helium atoms are not conserved. But for that to be actually observable, it would mean that you would need to have a superfluid in which helium atoms actually die.
This is not what I was.
Sorry.
I agree with what you're saying, but it's not what I had in mind. So there, in the helium case, you might want to remove second sound by relaxing the emergent U1. I mean, the emergent winding number symmetry, which is not a U1, it's a one-form symmetry, but anyway.
The one-form symmetry, yes.
So there you could do the same thing, and you would include dynamical vortices, etc. But at 0 temperature, if I were to go to 0 temperature, then vortices don't matter. And that symmetry, I mean, is restored up to the anomaly, and the anomaly generates for you second sound. So now if I move to solids, now I have these QIs, these emergent translation symmetries.
Okay.
And I don't know, let's pick, say, the transverse sector at 0 temperature. Why would I get rid of second sound there? What sense does it mean? I mean, could I get rid of second sound in a transverse sound in a solid at 0 temperature? Or the MIJ would just automatically turn off.
So transverse sound, different from, so second sound is the second longitudinal sound wave in a solid. So that's the thing that I'm killing here. Transverse sound just arises from spontaneous breaking of translations and rotations.
But do you make any distinction between that and transverse sound in this context?
Yes, absolutely. So transverse sound here, YIJ here describes the transverse and pressure waves that show up. This ZI has these extra hydrodynamic waves that are also longitudinal. So the reason it's called second sound isn't because it's actually there are only 2 sound waves of shear and longitude. It's the second longitudinal sound mode. So there's the shear wave, there's the pressure wave, and then there's the additional hydrodynamic longitudinal mode. So the fact that it's called second sound is just an artifact from superfluids that then applied here.
So you seem to say that somehow, so second sound in that context, it's because it's temperature waves.
Right, yes.
How does the fact that this is temperature waves come in your formalism?
So you can, if you actually find the dispersion relation here, you can see that temperature wiggles. After you impose,
sorry, let me ask it again. How do we see that the ZIs are the objects that somehow will naturally encode these temperature waves?
Okay, so essentially these zi's, there's a time-like vector that you can create out of the x mu's and the phi i's. So the x mu's, you basically compute dx mu d phi naught. So dx mu d phi naught gives a time-like vector. You can then just take the norm of that, and that gives you basically the fluid for velocity. Now, these psi i's here give you another time-like 4 vector. And the way that you do that is you look at d mu psi I, and notice that all of these are space-like vectors. And then there's one unique time-like vector that's orthogonal to these. So when that's the case, you now have these two independent basically 4 velocities. One describes the 4 velocity of the lattice, one describes the 4 velocity of the temperature. And the fact that these can oscillate independently of each other means that there's second sound. When we then gauge fix these phi I equals psi I, that forces these 4 velocities to be the same. And when they're forced to be the same, then there can be no second sound. There's just this one mode that propagates in the longitudinal.
So this is why in the ordinary formulation of solid hydrodynamics, there's no second sounds, because we never introduce 2 such time-like vectors.
Right, yeah, absolutely. Yes, and so temperature is then diffusive. And so if you go to higher order in the derivative expansion for this, you'll find that temperature is now diffusive.
Okay.
All right, thank you. As always, I appreciate the questions. I'm glad I could answer this one. If there are any other questions, please feel free to ask. All right. So, well, before I get to the end, let me just say one last thing, which is that I began by claiming that these symmetries here emerge for unbroken generators. And I imposed these symmetries with the tacit assumption that I always had a full set of unbroken translation generators. But notice that with solids, I don't have a full set of unbroken translation generators. I only have, if you kill off the QIs, which we ultimately do, then the only thing that we have is these P mu, is the PIs without the, is just these PIs if we kill off QI. So what we could have done from the beginning is just said, look, solids spontaneously break spatial translations. So let's, instead of giving these things, these generic time-independent diffs that are characteristic of unbroken translations, we can just give them ordinary shifts that would take into account the fact that they are homogeneous on large scales. So it would be this gauge symmetry to describe things. And we really could just do that from the beginning, start with a Coset construction with these reduced diffeomorphisms on phi, and remove these goldstones from the beginning. And with these reduced diffeomorphisms, we would then have different ways in which these objects would transform. And you could go through and calculate using the Coset construction once again to find just directly, without any sort of funky non-algebraic inverse Higgs constraints, you could directly compute this object. So I'm not going to take you through that because that would be rather tedious and would produce all of the same sorts of steps. But it is an option that you can do, and it follows the same kind of logic as the Coset construction. Okay. So,
Michael, can I ask yet again another question on the?
Absolutely.
So the QIs, they're emergent symmetries.
Yes.
If they're exact, I mean, or say if they're conserved, then you would have the second sound mode. If they're not, then you would just have an extra diff mode in the longitudinal vector. And you encode the non-conservation of these symmetries through this M term in the effective action.
Right, yes.
Now my question is, if I just take an ordinary zero temperature solid, should I expect to see second sounds? Because it looks like that this discussion is phrased, it looks like these M's, they should just vanish at zero temperature, and then I should see second sound emerge at zero temperature. But I don't.
So right? a conspiracy happens at zero temperature. It is absolutely true that these vanish, but at zero temperature, there's also no temperature, so there are no temperature waves.
I see. But the symmetries are still there. So
yes, the symmetries are still there.
Associated to them.
Right, yeah. Symmetries are still there.
So is it something like the associated static susceptibility vanishes at zero temperature? And so that those would-be modes just vanish?
Yeah, well, basically the way that these vanish is just that you can't write down these terms at zero temperature. Basically, this beta here, if you go to zero temperature, this is 1 over the temperature, so that diverges. So you basically, yeah, it gives you kind of
that I understand. But if I write, say, the effective hydrodynamic equations that derive from that action, and I would have an equation that corresponds to the conservation of these Qs with a side, which would be controlled by this M. Now I go to M vanishes essentially. But then you're saying that something also happens on the left-hand side, so that this extra conservation will vanish as well.
So,
or decouple.
No, basically what happens when so it is true that this is conserved. It's also true that T mu nu is conserved, but they're not independently conserved anymore at zero temperature. So essentially what happens for a zero temperature solid is, let's just transform to physical space-time. The only thing that happens is this G00 term vanishes. And so you just have stuff written in terms of these psi i's and derivatives of them. If you compute the, your action is basically just a function of G ij, which are constructive derivatives of these psi i's. So if you compute the stress energy tensor, and then you compute this J I mu object, the fact that they are both conserved are no longer independent statements. You can derive conservation of one from the other. In fact, if you have conservation of J I mu, those are just the equations of motion. And so that means that you can, from those equations of motion, compute the fact that T mu nu is conserved. So
here, the Ji is, this is the current associated with Qi.
Right, yeah.
Okay.
Yeah, so the conservation of Ji is just directly the equations of motion for this zero temperature object. And those are the only equations of motion at zero temperature. And so then those can be used to derive conservation of stress energy. So that's why you don't get these extra modes, just because there's this conspiracy that at zero temperature, they are not independently conserved.
All right, I'm gonna have to wrap my head around that. Thanks.
Okay, so to conclude, if you take away nothing else from this talk, take away these viewpoints. So for finite temperature systems, the hand wavy explanation for why you get these extra Goldstone modes is that the microstates of any sort of thermal bath will spontaneously break every symmetry. Just think about the most complicated state you can think of that exists in a microstate in a thermal bath, and so that will spontaneously break symmetries. However, the Goldstones that arise from these microstate spontaneous symmetry breaking are different from the ones that arise from the spontaneous symmetry breaking associated with the density matrix itself. And they differ in the sense of emergent time-independent gauge symmetries. So these arise at the level of these diffeomorphism symmetries that I call fluid diffs, just because they initially showed up in fluids. And then generalized chemical shift symmetries. Why they're called chemical shifts, I don't know. But this is the term that was come up with U1 symmetries. And so these are just the generalization of that. Now, when you construct an effective action with this coset technique, you have these expanded inverse Higgs constraints, which can remove extraneous goldstones and these unbroken fake goldstone modes as well. And the reason that these are expanded is just because these non-equilibrium actions are more complicated and you have these goldstones that are not actually goldstones. And finally, the ways that these cosets can be used and have been used to expand the known list of non-equilibrium effective field theories. They've been used to construct fluids, which were already known, superfluids, solids, supersolids, pneumatic liquid crystals, symmetric liquid crystals in phases A, B, and C, and plasmas and some other related objects to plasmas. So anyone curious about these can read these papers of mine. And yeah, I'd like to thank both my advisors at Columbia, where I just left, Alberto, Nicolas, and Landry, because they were very important in encouraging me, pushing me to do things, and also to Hong Lu, my advisor at MIT. Thank you also to you for inviting me, and I will take more questions if you have them.
Thanks a lot, Mike. Very nice talk. We had some questions, but we have time for some more, both formal and informal. So as usual, we are open for questions now, and then I stop recording in case somebody wants to just discuss. But let's see. We already had some questions.
Can I ask a question?
Yes, of course.
So, yeah, thanks for the talk, Michael.
Thank you.
I don't claim to have understood everything, but I tried to read along with what you explained. Let me try to understand one example, namely that of a vector valued condensate, which simultaneously breaks internal and space-time symmetries. So have you thought, I mean, I don't want to throw something completely new at you, but have you thought about some case like that? Because you were distinguishing these cases, right?
Yeah, so can you just quickly explain what is vector valued condensate?
Okay, so for example, a p-wave superconductor has a vector valued condensate where you have an expectation value, not just for like we have for a scalar field like the charge, like a charge condensate developing, but it's a like a gauge field that is condensing, if you will, or like your current develops an expectation value, if you will, and that flows in a certain direction, right? So that's singling out a spatial direction. So you at least if you think of it, then it's just the analog of the standard order parameter that you have from in a superconductor, but it's not scalar valued in space time. It is vector valued in space time, if that makes sense.
Okay. Yeah. So, well, in a certain sense, something of this sort necessarily has to exist in any condensed matter system. Maybe this is a particular case that has more subtleties, but like, for example, if you break boosts, you're going to have these. So these would break rotations as well, I suppose. So yeah, you should probably get some rotation goldstones. Now, they may be removable via some sort of inverse Higgs constraint. I would need to see the specifics of these cases. Also, yeah, sometimes you also do need to couple these goldstones to additional matter fields. So I don't know if those would show up here, but occasionally you do. For example, to describe a Fermi liquid, you need to couple these to some Dirac fermions, and you find other inverse Higgs constraints that come from these. But the fact that you have a system that spontaneously breaks symmetries I think means that you certainly should be able to apply the Coset construction. It may require some amount of thought to figure out exactly how this is supposed to go. But yeah, if you have references, you could send those to me. I'd be very happy to look at them.
Yeah, I just try to relate it to something that I know well, and just to understand the distinctions that you were making in your talk. Thanks. I like that's good explanation what you gave. Let me ask a different question to, if I may, like just since I'm talking already. So again, I'm still trying to understand this, so forgive me for maybe asking a very naive question, but so you kept the translation operators intact, right? So the pi and the p0, those were all the translations were symmetries, unbroken. So just naively, can I apply this formalism to a broken p0?
Yeah. So if you spontaneously break time translations, but let's say we do the same sort of thing where we have a U1 charge that is also broken, and there's this diagonal unbroken as well. What you will get is a superfluid. So essentially with the superfluid, you have this U1 charge that comes from particle number conservation. You have P naught, which is just time translation. You break both of these, but then keep P naught plus Q unbroken. And so this gives rise to superfluid behavior.
So if I just have a system a fluid that I can describe with hydrodynamics, and then break time translation invariance, it turns into a superfluid?
Yeah, as long as you also include this Q charge that is broken, but the diagonal is unbroken. If you don't have some sort of, because typically you want some sort of large scale time translation symmetry to hold. Otherwise, who knows what your system's going to do. But yes, if you have this specific spontaneous symmetry breaking pattern, then you get a superfluid.
Okay, thanks. It's very interesting. Thank you.
You're welcome.
Any other question? Okay. If not, let's thank Michael again. Ask you all to stay tuned for the program for the next year, and wish you happy holidays. So let me end the recording.